Previously, we have seen received bandpass signal correlation, where we tried to compute the correlation of received signal with itself. And on solving, what we get is three important expression, where this expression shows that the correlation of channel with itself depends on the correlation of Hi with Hi and the correlation of Hq with Hi. And also the correlation of received signal with itself is related to the correlation of the channel through the carrier frequency and real part of it. So we stated that in order to study this correlation of received signal, we need to have the correlation of Hi with Hi and the correlation of Hq with Hi. And we obtain that the correlation of Hi with itself is a function of zeroth order Bessel function of first kind, which is obtained when p theta is equal to 1 upon 2 pi. We assume this because of the Clark's model of 2D isotropic scattering, which states that all the rays that comes to the receiver, the angle of all the rays that come to the receiver is uniform. That is, the probability of theta is uniform along all the directions. And now we want to see what is the correlation of HQ with HI. And we saw that the correlation, this cross correlation is equal to 0 because this sign is an odd function. And so this integral comes out to be 0. So because of this, we can say that the correlation of the channel can be characterized by the correlation of in-phase component of signal. That means phi of HH of t is equal to phi HI of delta t. So if we know these, the property of this phi HI and HI, we know the properties of the channel, the correlation of channel, and from this correlation we can study phi RR of delta t. So now to study the correlation of channel with itself, we just need to study this figure, which shows the correlation of Hi of delta t. And this is J naught upon normalized by 2 pi. So in this figure, what we can see is this, let's say this value is 0.6. This 0.6 is obtained for a value x is equal to Fm delta t. And we can say that at this x, the channel is 0.6 correlated to itself, or you can say channel is 60% correlated to itself. Now, the interesting thing to see here is Fm is equal to V by C into Fc. And when we increase the velocity, this Fm will increase, and as a result, this x, to have a certain value of x, this delta t needs to be decreased. So now we can say when the velocity is increased, if 60% of correlation was obtained at delta t1, but now we're increasing the velocity, this delta t1 has now been decreased to delta t2. So with the increase in velocity, the time over which the channel is correlated is decreased. And this time, delta t, is called the coherence time. That is the time over which the signal is correlated to itself. So this we know that this RT we assume that this RT to be white sense stationary. So that means it is independent of time. So the coherence time does not depend on the exact time of the signal. Let's say this is the time axis and we have T1 and T2. The coherence time does not depend on this T1 and T2, but instead it depends on the difference between the T1 and T2. And the rule of thumb says the coherence time is equal to 0.423 upon Fm. Or to be exact, it is 9 over 60 by Fm. That is, it depends on the Fm. And Fm is a function of V by C Fc. Thus, it depends on V and Fc. So now if we see that, to have a more better understanding, let's say we have a signal fluctuating such that the signal undergo high fluctuations. Here the time over which the signal is correlated is probably this time. And if we consider the slowly fluctuating signal, now this correlation, the time over which the signal is correlated is increased. Let's say we can achieve this 60% of correlation at this delta t, which is, let's say, delta t1. And now for a slowly fluctuating signal, this delta t, and we also assume that, let's say, it achieves a correlation of 60%. And it can be observed that this delta t2 is far greater than delta t1. That means to achieve a 60% of correlation, the slowly fluctuating signal will have a coherence time greater than this highly fluctuating signal. So with this, let's move further, and we suppose that this is the signal, and this signal has a symbol duration of Ts. Now when this coherence time is greater than symbol time, what it means is that, let's say this is the coherence time and this is greater than the symbol duration, then these 2 points, they are correlated to each other. So that means we say that the channel is fluctuating very slowly. As a result, we have a slow fading channel. But however, on the other hand, if we say that this Tc is less than equal to Ts, let's say this is the Tc, let's say this time is Tc. So now we can say these 2 points, they are not correlated because the channel is changing very quickly. So instead we call it as fast fading channel. So with this, we have studied the time selectivity of the channel, which depends on the coherence time and symbol duration. So once we have this coherence time Tc, we can get whether the fading is slow fading or it is fast fading. And the examples of this slow fading is like when we have very low velocity. For example, let's say this symbol duration is 2 millisecond, or let's say it is 1 millisecond, and this coherence time is 2 millisecond. So this is slow fading scenario. But let's say when we increase the velocity of the receiver. So once we increase the velocity of the receiver, the FM will increase, and since TC is directly inversely proportional to FM, this TC will decrease. And now let's say this TC has been decreased to 0.5 millisecond. Now the situation has now been changed. So TC is now less than equal to TS, which is 1 millisecond, and this is 0.5 millisecond. So from this example, we have seen that how the increase in velocity changes the channel from slow fading channel to a highly fluctuating channel, that is fast fading. Now again, the advantage of having this slow fading is that, so let's say we transmit a single duration of X. Now in a flat fading, we know that the channel coefficient gets multiplied with the symbol. And of course we have AWG and noise, and this is Y. So for slow fading, this H will remain same over the symbol duration. So that means if we want to recover X, we can directly recover it using estimating the channel and taking its inverse. But whereas in case of fast fading, if we assume this is the symbol duration, and let's say channel has been changed 2 times, here the channel is H1 and here the channel is H2, then in this case we have Y is equal to H1 of X times 0 to T1. Let's say this time is T1 plus H2 of X T1 plus some time delta minus the symbol duration. This is the symbol duration TS. So for this expression, we need to have an advanced equalizer. So if we try to design a system, we want our system to experience slow fading rather than fast fading, because for fast fading we need to have an advanced receiver to handle the fast fluctuation of the received signal strength. So with this, we have studied the coherence time, that is the time over which the signal is correlated to itself, or we can say the channel is correlated to itself. Both the things are related to each other. We have seen that earlier. Both the things, signal and the channel, they are related to each other through carrier frequency and the real part of it. And then we have seen the time selective of the channel. Now once we have this coherence time TC, we can compute whether the channel is slow fading channel or fast fading channel.